boundary value problems using the unified transform method.
Thank you. I want to, just like I think all of the speakers so far, I want to extend my thanks to the organizers both of the program and of the workshop. It's been an excellent week. Although I have to admit I've been spending a lot of it this week on frantically preparing this talk. So it'll get more relaxed next week. And also because Nick is no longer here, I get to use the laser pointer. So this is joint work with Jorge Cisneros, who's a PhD student at University of Washington. Jorge is also supported by a Ford Foundation Fellowship. Everything, all of the good results you're going to see on these slides are due to Jorge, and then if you see any typos, those are due to me. Okay, so what is the long-term goal? And we're not close to this long-term goal. The long-term goal is to solve initial boundary value problems for quasi-linear PDEs. So those are, well, actually this is a little bit more restricted than quasi-linear because I want this coefficient to be constant. But I'm looking at PDEs, nonlinear PDEs of the form time derivative, and this could be a vector, so these could be systems. Time derivative is equal to highest derivative in this herd of right-hand terms. This is the alpha term. And then lower order terms, and that could be nonlinear. Okay? And I want to do that using finite-difference methods. Of course, you can get a lot fancier than that, but those methods are still very popular. And so I want to figure out what we can do for boundary value problems. For second order and lower, so for first and second order, we kind of know what to do. Using mirror principles or other ideas, basically, because we know the exact solution for nearby problems, namely nearby would be just this. Based on reflection principles, we can, when we need ghost points, we can introduce the values at those ghost points and deal with that appropriately. That becomes a little bit harder when you have non-homogeneous boundary conditions, but it can still be done. Okay. If you extend those ideas heuristically by extending across boundaries and introducing ghost points and values at those ghost points in a similar way as what you would do, say, for n equals 2, then you typically end up making significant errors at the boundaries. And so we'd like to know what we can do better than that. So the idea is, and so this is the part that we're nowhere close to, is a split step method. So let's see what we can do about the linear part. And when I say the linear part, I really mean that alpha term. So let's see what we can say about this. Use that to advance a linear step, and then later on use some standard method to deal with the nonlinear step. The point is that when you're looking at this term, and it's finite difference approximation, that's going to have the widest stencil. So this is, in finite difference land, this is the most non-local term, and it's going to be most affected by what's happening at the boundaries. Right? Any other effects on the boundaries of all of these other terms is going to be secondary to what happens here. So if you can do this from the point of view of the boundary value problem correctly, that should be a very positive thing. So today I'll talk specifically about that first step. Okay, so the idea is, so I'll talk a little bit about the unified transform method later, but so what we want to do is I want to discretize this in space, and so I'm going to go from Q to Qn, and once I have this discretization, I included triple dots here. For everything I'm going to talk about today, I can do anything that would correspond to constant coefficient linear. Okay, but as I already hinted at, from the point of view of the split step idea, really if I can deal with that first term, that would be the most important part. Okay, solve this discretization, which would give us Qn of t analytically using the UTM for all positive time. The formulas that you'll see, hopefully I'll get there, are complicated. They're messy. It's not something that you would say, oh, that's going to be the first step in the split step method, because that would be horrendously costly. So then the next step after we do this would be to come up with a small t approximation for those UTM formulas that we get. that should be something that's significantly simpler, and that then could be coupled with a standard nonlinear solver. A evolution problem for the nonlinear terms. That part we also don't have yet. Okay. So let me talk a little bit about the unified transform method. I think that there were some talks in previous workshops about this, but again, that was a different workshop. I guess this goes back to 1997, where the first results were published. Fokas' original goal was to solve, was to extend the inverse scattering method for KDV, nonlinear Schrödinger, and so on, to boundary value problems. Okay. Now, if you have any experience with the inverse scattering method, it's not simple. It's simple if you restrict yourself to soliton solutions, and it's not simple if you go beyond that. So it's very messy, so it should not be a surprise to you that if you're going to extend it to boundary value problems, it's going to get even messier. Okay, so it's a very complicated method, very powerful when it can be applied. And it can be applied to integrable problems. Now, one class of integrable problems that we are far more comfortable with is constant coefficient linear problems. Constant coefficient linear problems are integrable. And if you look at the UTM in that context specifically, it simplifies significantly to the extent, for instance, that it could be taught to undergraduates. And I've done that, other people have done that, so this is doable. Okay, and so the key ideas which you'll see once we get to the specific examples is, I've already mentioned the mirror principle for second order problems. There you use the symmetries in the physical space. So you have that the equation, for instance, is invariant under the transformation x going to minus x. Okay, fine. But if you had a third order problem, you lose that. Okay? So the key idea is really that instead of using the symmetries of the equation in physical space, you'd want to use the symmetries of the equation, well, symmetries of the dispersion relation associated with the problem. Now you're in the complex plane. You can look at those symmetries. You can see how they impact the problem. And then combined with some analyticity properties, with contour deformation, you can actually get exact solution formulas for arbitrary linear constant coefficient boundary value problems. If you apply this to a problem where there is a classical solution formula available, with a little bit of more deformation, you can show that you retrieve the classical solution formulas. But in other cases where there is no classical result, you get new results. That's for the continuous in x, continuous in t transform. If you're looking at, so what I want to do is I want to look at semi-discrete. So I'm going to discretize in space, but I'm going to leave t continuous. So the only work really that addresses this is Biondini and Wang in 2010. Most of what they talk about is second order. There's one example where they do a third order problem. But they look at this in its own right. They don't think of this as necessarily coming from a discretization for a continuous time problem. So given what we want to do with this, we definitely want to leave the small parameter h, which is our spatial discretization. We definitely want to leave that into the problem. We are always interested in what's going to happen in the continuum limit, which is something that they lose not having that parameter around. So our goal is really to start with a continuous problem, well posed, sufficient number of boundary conditions at all boundaries, and to discretize that. And so not only are we going to have the small parameter h there, we're also going to have our boundary conditions for the semi-discrete problem will have to be inherited from the continuous setting. And we'll have to figure out how to do that. Okay? And so that's also what is hinted at here. You know, it might be very tempting to say, let's use a 17th order stencil, and then, oh, but I only have one boundary condition. Well, now, in order to make everything work near the boundaries, you have to invent a lot of stuff. And how do you invent it? Can you invent it consistently with the information that's given in the continuous case? Or what do you do? Okay. So let me show you some pictures. This is for the advection equation. Now this is a cheat because this is not much of a boundary value problem, right? I'm solving this on 0 to 1. So this is, stuff is moving to the left. So I need to give you something, I need to give you a right boundary condition, stuff to flow into the domain, and nothing on the left boundary. Although this is a very simple problem, it allows me to set the stage for some of the more complicated things we'll see. So what you're looking at is, again, this problem with a two-hump initial condition, and then the boundary condition that's provided on the right boundary in this case is actually fully consistent with the initial condition that's given. So this is really pretending to be a half-line problem, just with a window from 0 to 1. There are, I hope it's semi-visible, there are 5 methods that are compared on these pictures. So this is, these are time slices, time equals 0 to time equals a quarter. So you see stuff is going to the left. The exact solution, which of course we have in this case, is the black curve, which is more or less underneath the green curve. Are the colors showing up at all? Okay. There's a couple of other, so the green curve is obtained by using the unified transform method and then evaluating it at the appropriate time. Okay. Whereas the other colors, I have forward Euler, I have Runge-Kutta 4, I have backward Euler, and I have trapezoidal, are all compared here. If a certain color doesn't show up, it means we've not plotted it because it was just too bad. I mean, it just looked like a big mess. So one of the things to notice is that green and black do pretty well. And then, for instance, trapezoidal, which is the dark blue one, is the one that's typically creating all of these oscillations, which is also pretty much old news for people who work with these things. And then, for instance, backward Euler, you see a lot of dissipation. And then the ones that are basically not plotted are forward Euler and Runge-Kutta 4 explicit methods, which, other than for very small times, already have problems. So for these plots, so full disclosure, what we have is a fixed time step, and then we're looking at a range of spatial steps. Okay, so.
What stencil did you use in space?
Oh, so that one was, you'll see it later as well, but this is just a first order approximation of the spatial derivative. So qn plus 1 minus qn over h.
Oh, so the first order.
Yes. And part of that is, of course, determined by how many boundary conditions we have, and therefore can take into account discretely. So let me explain this plot. You'll see a couple more plots like this. So this is, as I said, a fixed time step. And so here you see the results for the different methods that I mentioned: forward Euler, Runge-Kutta 4, backward Euler, trapezoidal, and then also UTM. So for UTM, exact solution formula evaluated at the time steps we were interested in. And then for the other methods, it's the semi-discrete approximation then solved with the method of lines with this method for the time discretization. Okay. It should not surprise you at all that forward Euler and Runge-Kutta 4 on these plots, by the time I get to about -2, are off the picture. So this is a L infinity error plot. Because they're explicit methods, there's a CFL condition, and I'm violating the CFL condition if I'm going too far to the left. Okay, so one of the main things to take away from this plot, or maybe the main thing to take away from these plots, is that the evaluation of the UTM at specific time steps, of course, does not have any CFL condition at all. So that's a beneficial thing. What you're seeing here with backward Euler and trapezoidal is their errors are, of course, leveling off, because at some point, because we have the fixed time step, what you're seeing is just the error in the time discretization. Okay. You should also notice that this straight line right here is order 1/2. I should get order h instead of order h to the 1/2. There's another plot that I didn't include, that if you go to smaller times, if you go to smaller h, you do see that. But one thing that indicates is that the continuum limit from the semi-discrete UTM solution to the exact solution of the continuous problem is actually rather slow. Okay. So let's actually do something more interesting. So not a transparent boundary. So here's an initial condition plotted right here, and here is again on the same equation. So again on the right, a boundary condition So what you'll see in the plots on the next slide is we'll start like this, and then this is moving in from the right. Okay? So black is, again, the exact solution. And then the green is doing by far the best. That's why, of course, I'm including it, right? But then the other thing to notice is that the other methods either have a ton of dissipation, backward Euler, or just don't even come close to matching the magnitude or the location of the peaks. Okay, so a lot of that's compiled in here. So similar to what you have, this is actually very similar to the previous error plot. Again, you have backward Euler and trapezoidal leveling off because of the time discretization. And then in this case, still for these values of h, it looks like you're getting h to the 1.5. Although here you can already see this is bending back, and that actually turns out to be the order h, which I didn't include. Okay, more interesting. So now that we know how to look at these plots, now I'm going to look at the, in my world, I would call this the linear nonlinear Schrodinger equation. But the linear Schrodinger equation with this initial data and Neumann boundary conditions, constant Neumann boundary conditions on both 0 and on 1. Okay? And I've plotted the real, the imaginary, and the modulus squared at t equals 0.5 for all of them. And then here again you see the infinity error plot, very similar to what you have before. All right, so let's actually start going into the details of what we can do with the UTM. Again, I don't need the UTM to solve this problem at all, but I will use it on this problem just to outline the steps that we have, and then we'll apply it to a more complicated third order problem. So my continuous problem is this, and so then the stencil I'm going to use is this semi-discrete problem. I should also say for the examples I'm showing you, I'm only going to do half-line problems. I'm not doing finite interval problems. Because the formulas are about twice as long for, with every boundary I introduce, I get a lot more terms. Okay? So, but conceptually, the sequence of the steps is exactly the same. Okay, so here is my stencil that you asked about. And so because I have a positive C and I have a semi-infinite line problem, I don't have any boundary conditions to prescribe. Okay, so how does the UTM, the semi-discrete UTM work? So we'll need, just like you need a Fourier transform pair for the continuous problem, I need a semi-discrete Fourier transform for this problem. So here is my forward transform, and here is my inverse transform. One of the things that we noticed is if we are given Dirichlet boundary conditions, so in other words, if we know Q0, then it's actually far beneficial to start at 1. Okay, otherwise we end up with a bunch of Kronecker deltas when we do inversions, and it just becomes annoying. But that's a small technicality. Okay. So this is the equation I've discretized. So now everything is starting from here. So here is the equation rewritten with now an auxiliary parameter k being present in here. Okay. So if you work out this time derivative, and this is a forward difference, this is the expression you see evaluated at n plus 1 minus the expression you see evaluated at n. If you just work out both sides, you get, after canceling out the exponential, you get exactly the equation on the previous slide, and you'll also have recovered the dispersion relationship right here. I should emphasize that if you're used to dispersion relationships in, say, dispersive equations, there's a factor of I different in how it's used in the Fokas method. Okay, so here's our dispersion relationship. You can see, so I don't have an I there. Okay, if you of course let your limit as of h going to 0, then you're going to get the just c times k here back for the continuous problem. Okay, so I call that the local relation because it's still evaluated at an n and at a t. And then the next major step is to go to the global relation. So you get the global relation by just integrating over all time up to a certain level, and then by integrating or summing, in this case, because it's discrete, over all space. And what I get, using my definitions of my Fourier transforms, this equation can now be rewritten. When I say local relation, I mean this minus this is equal to 0. this can be written as in this form, and then because of where our Fourier transforms are defined, this is valid in the lower half plane, okay, because I'm on the half line. And there's this f0, oops, there's this f0 that appears in here, and it's given here coming from this time integration over, it's going to be a boundary term because I'm summing over all n. Okay. So what does the global relation do is it provides a relationship between the solution at capital T, that's what this is, the initial condition, and then boundary terms. Now, as we've already said, for this specific equation on the half line, I should not need any information from the boundary. So one interesting thing is to see how we get rid of that. Okay? But the typical thing that's going to happen in the UTM is when you do your integration, or in this case summation, over all n, and then integrate up to a certain capital T, what you'll get is as many boundary terms on each side as the order of the equation. Okay? That's double the amount that you should have to provide. Okay, so if I have a finite interval problem, I should, of order n, I should have to provide n boundary conditions, and this is going to give us a relationship between two n boundary functions. Okay, so the main key is how do we get rid of this? So from this global relation, if I solve for this q hat at capital T and then Fourier invert, I end up with what I'm calling the quote-unquote solution formula. Yes, it is a correct expression for the thing that I'm looking for, but it's kind of useless because it depends on things that I don't know. Okay, so it's not really a solution formula. The next step of this UTM machinery would be to examine the symmetries of the dispersion relationship. And with the dispersion relationship I gave you a couple of slides ago, so what I'm looking for is what are the transformations that I can do on K that leave the dispersion relationship invariant. Okay, and in this case, it's a little calculation. You find out that the only symmetry is the trivial symmetry, namely nu is equal to k, so we're not doing anything. And then, of course, I should say, because we're in the discrete setting, there's also periodic analogs. Okay, so everything is defined up to, I think it's I pi over h. Okay, but that doesn't help us anything. Okay, so that means that since this is only the trivial symmetry, I'm not going to be able to do much with this, but we expected that for this simple problem. Okay, the next step would be typically you would use these symmetries to get rid of some unwanted terms. I don't have any symmetries to use in this case, so in this case this unwanted term disappears in a different way. For our left-going wave equation, we have that the real part of the dispersion relationship, you can check, is positive in the upper half plane, and then by contour deformation I can show that this term simply vanishes. Okay, which means that my solution formula, no quotes anymore, is now just this. And then if you do a little bit of algebra, you can relate this back to the typical advection solution that you would get. Okay, if I were to do the advection equation going to the right, so with C negative, of course I need to use a different stencil. Now the boundary condition does matter, and your formula would be, same term coming from the initial condition, but now I would get a boundary term which does not vanish in this case, because now the W, the real part, would be negative in the upper half plane, and I wouldn't be able to deform to eliminate that term. Okay, so that was a straightforward example. Let's make it a little bit more complicated. So third order. So linear KdV. Okay, this is a problem that you can't solve using standard methods. Okay, also in the continuous case. So it turns out, and this may not be clear, but let's just go with it. It turns out that for this problem, again I'm solving this on the half line, you need to provide two boundary conditions on the left. Okay. If the sign was different, I would only have to provide one boundary condition. Okay, so with these two boundary conditions, that's a Dirichlet and a Neumann condition, one of the things that I'll have to do is I'll have to figure out how to suitably discretize them so that I can still solve my semi-discrete problem. That was what I said, and I want to go from a well-posed continuous problem to a, I guess, well-posed semi-discrete problem. Okay, I don't want to have to invent boundary conditions to deal with this. The stencil I'm going to use is this one. You could come up with other choices. And so it's very clear what I do with the initial condition. I just sample it at my discrete spatial points. And then for the Dirichlet condition, also easy. And then I'm not quite clear on what to do with the Neumann condition yet. Okay, so we'll have to figure that out. The local relation, a little bit more complicated than last time, but again, if you work out this time derivative and if you work out this difference and you use this dispersion relationship, then after canceling out the exponential, this mess simply becomes what we had on the, simply becomes this. Okay? But now we've bought this parameter k in here, which we can use. That's going to be our Fourier variable. Okay. The global relation, again, sum over all n, integrate over up to capital T, you get this, which now relates your solution to your initial condition to this is now a boundary condition that I don't know because this is at a ghost point. This is outside of my domain. Okay, so what do I do with that? My Dirichlet condition, or sorry, integral of my Dirichlet condition, and then something that is given at the first node, which I also don't know. Okay. So the solution formula, quotes, would, again, you solve this for the Q hat, invert your Fourier transform, you get this, and I get a solution depending on too much boundary information. Okay, so at the moment I know this. So now step 3 prime. Now I know what to do, or now I know one of the things I can do with my Neumann boundary condition. I want to discretize it in such a way that I do not introduce new unknowns in here. This tells me I need f minus 1, f0, and f1. So as long as I discretize my Neumann condition involving only nodes minus 1, 0, and 1, I'm not introducing new unknowns. So all of those would work. In this case, because that was a first order stencil, I'm just picking a first order discretization for the Neumann condition. Okay. After multiplying by an exponential and integrating, I get this relationship between the f's. So the capital B is given. And so now I can use this to eliminate f minus 1, which means that in my quote-unquote solution formula, the only thing I don't know yet is f1. So I need to get rid of f1. Okay. Next step, the symmetries of my dispersion relationship. They're messy. They're more messy than in the continuous problem for sure, but you can still get them. Here they are. And you have to be careful with branch cuts. I don't need to tell this audience that. So now, with these non-trivial, there's of course also the trivial symmetry, but with these non-trivial symmetries, I can now go back to my global relation and evaluate it at, instead of at k, I can evaluate it at nu1 of k or nu2 of k. The reason for doing that is that it's, things change over here, but because f minus 1, f0, and f1 only depend on w and not on k, they stay invariant. So when I evaluate these at nu1 of k and nu2 of k, I'm not introducing different unknowns. Okay, so of course they are now valid in different regions. Previously I was valid where the imaginary part was negative. Now this is valid where the imaginary part of nu1 or nu2 is negative. And if you plot those regions, you get this. So in the blue region, the imaginary part of nu1 is valid, so that first extra global relation is valid. In the brown region, the other one is valid. And then there's one region where they are both valid. But here's our integration path, right? Minus pi over h to pi over h. So you can see that in order to eliminate the boundary condition f1, right, that's the unknown I don't have yet. If I had blue everywhere on this line, I could use one of those global relations to eliminate a boundary condition. And then maybe I can still do something else with the other one. But you can see that in order to eliminate f1 for negative k, I'm going to have to use one global relation. And in order to get rid of f1 for positive k, I need to use the other global relation. So despite the fact that I have two equations to use, because of where they are valid, I only get to eliminate one boundary condition. That's why I needed to start with 2. Okay? If you change the sign on the equation, then actually both global relations are valid on the real line, and I can eliminate 2 boundary conditions. Okay? So that's, this is one of the ways to see how many boundary conditions you need to start with. Okay, so having eliminated, so we can use this to eliminate f1. Let's go back to, so f1 is over here. Let's go back to our solution formula right there. Now, one of the things that you're doing is, if you're using these new global relations to eliminate F1, so solve this for F1, you're going to bring in this. You're going to bring in Q hat evaluated at the new symmetries. And so that's something that you don't want in your solution formula. And so then the last step, and maybe the most magical step in the Fokas method, is by some more contour deformation, you can show that those contributions go away, which I've just summarized right there. I'm not showing you any calculation for that, but they do. Which means that my final solution formula of this problem, which cannot be rewritten in a series form or in any classical form, is given here. Okay? So I'm out of time, so I'll just say what are the next steps that we want to do. We want to, as I said, evaluate these complicated formulas for small t, so we can hopefully use them as a first step in a split step method, and then combine it with a nonlinear step. Here's some references. Thank you.
Does this approach preserve the invariance?
Does it preserve what?
Invariance.
Like,
energy.
well, so when you're going to talk about conserved quantities for boundary value problems, there's boundary effects, right? So already if you say, for instance, look at KdV on the half line, most of your conserved quantities are gone, because in order to show that they're conserved quantities, you have to do the integration by parts. That brings in boundary terms. Typically, you're toast. So I guess my answer to your question is I don't think your question makes sense. Sorry to phrase it that way, but yeah. That's right. Well, the motivation is that we want to solve nonlinear, non-integrable problems, right? Which are quasi-linear, so which have that first term. And then if I can understand what to do with that first term, it's going to be the most non-local one in terms of the finite difference approximation. Then I can now use the same stencil to go after the other stuff, right? The other thing kind of related to what you're saying is evaluating. I showed you the error plot for the third order problem as well. What am I comparing with? I'm comparing with the solution obtained using the continuous UTM, and the numerical evaluation of that is very non-trivial, but that's a separate talk.